Testing. This video is unlisted right now. Can you hear me? Okay, this is public now. All right, so I'm going to be reading about computer architecture. This is the book I chose. It is a free book. It's a CC by NT. It's like Creative Commons, but non-derivative. Free to distribute, free to use and distribute even commercially, but no derivatives. Uh, and yeah, this is the book I will read. So let's just get started. The text are very small. Should I? I think this is big enough. Welcome to the exciting world of computer architecture. Computer architecture is the study of computers. We shall study the basic design principles of computers in this book. And I will make notes and then send this Excalibur in the comments. I wish we could bold the text. The field of computer architecture is a very fast moving field, and every couple of years there are a plethora of new inventions. Okay, let's just skip to the definition. Architecture, the view of, of a computer presented to a software designer, organization, the actual implementation of the computer and hardware. I should start making notes here. Organization, architecture. Computer architecture is a beautiful amalgam of software concepts and hardware concepts. You design hardware to make software run efficiently. Concomitantly, we also design software keeping in mind the interface and constraints presented by hardware. What is this word? Wait.
Concomitantly.
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 At the same time or simultaneously. And what's the other? Amalgam.
Amalgam.
Amalgam. A mixture or a blend. concomitantly,
concomitantly,
concomitantly. Let us now answer the following question. What is a computer? What it can do, what it cannot do, and how do we make it do intelligent things? Let us start over some basic definitions. The first question we need to answer is what is a computer? Well, to answer this, we just need to look around us. We are all surrounded by computers. Yeah, but that doesn't define what it is. Each computer is programmed differently and processes different kind of information. MP3 player processes music files. So definition 2. Why is this in red? Computer is a general purpose device that can be programmed to process information and yield meaningful results. General purpose. Should there be a comma here? Because this browser is saying that that's a mistake. Note that there are three important parts to the definition as shown in figure 1.1. The computer, information store, and the program. The computer takes an input as a program, figure 1.1, and in response performs a set of operations on the information store. At the end, it yields meaningful results. A typical program contains a set of instructions that tells the computer regarding the operations that need to be performed on the information store. Information store typically contains numbers and pieces of text that the program can use. Let us consider an example. A typical program contains a set of instructions, and we have the information store. Contains a set of instructions regarding the operations that need to be performed on the information store. Information store typically contains numbers and pieces of information that the program can use. You know what I will do? I'll take this, copy here, then copy this. Can I bold it somehow? Like, never mind. There. And then we have results. Here is a snippet of a simple C program. So A is 4, B is 6, C is A plus B, and then print C. Computer will produce the output 10. This C program contains 4 statements. Here, each statement can be conceptually be treated as an instruction. Each statement instructs the computer to do something. Statements 1 and 2 instruct the computer to assign the variables A and B, the values 4 and 6, respectively. Statement 3 instructs the computer to add A and B and assign the results to variable C. Finally, statement 4 instructs the computer to print the value of C. Given the fact that we have defined a computer as a sophisticated device that follows the instructions in a program to produce an output, let us see how it can be built. Modern day computers are made of silicon based transistors and copper wires that connect them. However, it is absolutely not necessary that computers need to be built out of silicon and copper. Researchers are now looking at building computers with electrons and photons and even DNA. If we think about it, our own brains are completely powerful computers themselves. They are always in the process of converting thoughts, which are programs, into actions, which are outputs. So yeah, the CPU, the memory, and the hard disk. Let us now open the lid of a desktop computer and see what is inside. There are three main parts of a typical desktop computer: CPU, okay, main memory, and hard disk. The CPU is also referred to as the processor or simply machine in common parlance. We'll also use the terms interchangeably in this book. The CPU is the main part of the computer that takes the program as input and executes it. It is the brain of the computer. The main memory is used to store data that a program might need during its execution. For example, let's say we want to recognize it, all the faces in an image, then the image will be stored in main memory. When we turn off the power, the processor and main memory lose all their data. However, the hard disk represents permanent storage. We do not expect to lose our data when we shut down the system. This is because all the programs, data, photos, videos, and documents are safely backed up in the hard disk. Why does this hard disk look very strange? Figure 1.3 shows a simplistic block diagram of the three components. Along with these main components, there are a host of peripheral components that are connected to the computer. For example, the keyboard and mouse are connected to the computer. They take inputs from the user and communicate them to programs running on the processor. Similarly, to show the output of a program, the processor typically sends the output data to a monitor that can graphically display the results. It is also possible to print the result using a printer. Lastly, the computer can be connected to other computers through a network. A revised block diagram with all the peripherals is shown in figure 1.4. Hard disk, memory computer, hard disk, memory computer, and computer connects to all of this. Three CPU. We have the CPU. We have the main memory. And hard disk represents permanent storage. Hard disk is for permanent storage. Yeah. Hard disk is for permanent storage. Now, hard disk, memory, computer. I think I'll draw arrows like this. And then we have computer to memory. Normally I use a tablet. I'm using a mouse over here. And then computer to keyboard, monitor, mouse, and printer. Wait, actually, I should just open my tablet. Because I'm gonna be drawing arrows and stuff. It's gonna. Wait, in the copyright, they said no derivatives, right? Would this count? Hold on a minute. Do study notes count for no derivatives? Okay, I will, right then. Computers are dumb machines. Irrespective of the underlying technology, a fundamental concept that we need to understand is that a computer is fundamentally a dumb machine. Unlike our brains, it is not endowed with abstract thought, reason, or conscious. How do we make a dumb machine do intelligent things? Computers are tireless machines that can keep on doing calculations very quickly without ever complaining about monotonicity of the work. As compared to computers, our brains are creative, tire easily, and do not like to do the same thing over and over again. An instruction is defined as a basic command that can be given to a computer. We observe that to communicate with a computer, we need to speak its language. This language consists of a set of basic instructions that the computer can understand. Computer is not smart enough to process instructions such as calculate the distance between New Delhi and the North Pole. However, it can do simple things like adding two numbers. Programmers typically write programs in a high level language such as C or Java. Is C even high level? Isn't C like low level? No, low level is assembly. C is like mid level, right? These languages contain complex constructs such as structures, union, switch case statement, classes, and inheritance. These concepts are too complicated for a computer to handle, hence, it is necessary to pass a C or C program through a dedicated program called a compiler that can convert it into a sequence of basic instructions. A compiler effectively removes the burden of creating machine readable code from the programmer. The programmer can concentrate only on the high level logic. Program, compile, and then output. The The compiler takes the high level program as input and produces a program containing machine instructions. This program is typically called an executable or binary. Let us now come to the semantics of instructions themselves. The same way that any language has a finite number of words, the number of basic instructions, rudimentary commands that a processor can support have to be finite. This set of instructions is typically called the instruction set. Some examples of basic instructions are add, subtract, multiply, logic, or logical not. Note that each instruction needs to work on a set of variables and constants and finally save the result in a variable. These variables are not programmer defined variables, they are internal location within the computers. We define the term instruction set architecture as the semantics of all the instructions supported by a processor is known as the instruction set architecture. This includes the semantics of the instructions themselves along with their operands and interfaces with peripheral devices. Yeah, I don't know if I'm allowed to make notes or not. I'll search that online. Uh, But if I am, then I think next team I will start making notes. So semantics of all instructions supported by a processor is known as an instruction set architecture. This includes the instructions themselves along with their operands and interfaces with peripheral devices. The instruction set architecture is the way that software perceives hardware. We can think of it as a list of basic functions that the hardware exports to the external world. It is the language of the computer. For example, Intel and AMD CPU use the x86 instruction set. IBM processors use the PowerPC instruction set. HP processors use the PowerRISC instruction set, and ARM uses the ARM instruction set, or variants of it, such as Thumb1 and Thumb2. It is thus not possible to run a binary compile for the Intel system on an ARM based system. The instruction sets are not compatible. However, in most cases, it is possible to reuse the C program. To run a C program on a certain architecture, we need to procure a compiler for that specific architecture. Let us now begin the difficult process of designing an instruction set for a processor. Why does it say 20 over here? You can think of an instruction set as a legal contract between the software and hardware. The ISA should be able to implement all user programs. This is an absolute necessary requirement. We want an ISA to be able to represent all programs that users are going to write for it. For example, if we have an ISA with just a add instruction, then we will not be able to subtract two numbers. I mean, if the second number is a negative, if one of the numbers is a negative, then you can use the add, right? To implement loops, the ISA should have some method to re-execute the same piece of code over and over again. Without this, support for and while loops and C programs will not work. We should ideally not have a lot of instructions. We should see in chapter 9 that it takes a fairly non-trivial amount of hardware to implement an instruction. Implementing a lot of instruction will unnecessarily increase the amount of transistors in the processor, increase its complexity. Consequently, most instruction sets have somewhere between 64 to 1000 instructions. For example, MIPS instruction sets contain 64, while Intel has roughly 1000 instructions as of 2024. 1000 is considered a fairly large number for the number of instructions. Most of the common instructions and programs are simple arithmetic instructions such as add, subtract, multiply, divide. The most common logical instructions are logical and, or exclusive or not. Hence, it makes sense to dedicate an instruction to each of those common operations. It is not a good idea to have instructions that implement a very daily used computation. For example, it might not make sense to implement an instruction that computes arcsine. It is possible to provide a dedicated library function that computes arcsine using existing mathematical techniques such as Taylor series expansion. Since this function is rarely used by most programs, they will not be adversely affected if this function takes a relatively long time to execute. Let us assume that we have a lot of programs that add a sequence of numbers. To design a processor especially tailored towards such programs, we have several options with regard to the add instruction. We can implement an instruction that adds two numbers, or we can also implement an instruction that can take a list of operands and produce the sum of the list. There's clearly a difference in complexity here, and we cannot say which implementation is faster. The former approach requires the compiler to generate more instructions. However, each add operation executes quickly. The latter approach generates a fewer number of instructions, but each instruction takes longer to execute. We can implement an instruction that adds two numbers, or we can also implement an instruction that takes a list of operands, reduces the sum of the list. Latter approach generates fewer number of instructions, but each instruction takes longer to execute. Former type of ISA is called a reduced instruction set. The latter is called complex instruction set. A reduced instruction set computer implements simple instructions that have a simple and regular structure. The number of instructions are typically a small number, like 64 to 28. R, ARM, IBM PowerC, and HP PowerRISC. A complex instruction set implements complex instructions that are highly irregular, take multiple operands, and implement complex functionality. Secondly, the number of instructions is large, typically more than 500, like Intel x86. The RISC versus CISC debate used to be very contentious issue till the late 90s. However, since then, designers, programmers, and processors vendors have been tilting towards the RISC design style. Consensus seems to go for few relatively simple instructions that have a regular structure and format. It is important to note that this point is still debatable, as RISC instructions are sometimes preferable for certain type of applications. Modern processors typically use a hybrid approach where they have a simple as well as complicated instructions. However, under the hood, CISC instructions are translated into RISC instructions. Hence, we believe that the scale tilts slightly more towards RISC instructions. An ISA needs to be complete, concise, generic, and simple. It is necessary to be complete, whereas the rest of the properties are desirable. We have currently considered the following concepts. Computers are dumb yet ultra fast. Instructions are basic rudimentary commands used to communicate with the processor. Compiler transforms a user level program to a program consisting of basic machine instruction. The instruction set architecture refers to the semantics of all the instructions supported by a processor. The instruction set needs to be complete. We will look at the conditions that ensure the completeness of an ISA. We will then try to create a concise, simple, and generic ISA in Chapter 3. How do we ensure that an ISA is complete? This is a very interesting, difficult, and theoretically profound question. The problem of finding if a given ISA is complete for a given set of programs is a fairly difficult problem and is beyond the scope of the book. Given an ISA, can it represent all possible programs? We will need to take a recourse to theoretical computer science to answer this question. Casual readers can skip sections 1.6.1 to 1.6.6 without any loss of continuity. Okay, let's just skip read this. Towards a universal ISA. What's the star over here? Let us try to answer question 3. Assume that we are given ISA that contains a basic instruction add and multiply. Can we use this ISA to run all possible programs? The answer is no, because we cannot subtract two numbers using the basic instructions that we have. If we add the subtract instruction to our repertoire of instructions, can we compute the square root of a number? Even if we can, it is guaranteed that we cannot do all types of computations. To answer such vexing questions, we need to first define a universal machine. A machine that can execute any program is known as a universal machine. It is a machine that can execute all programs. We can treat each basic action of this machine as an instruction. Thus, the set of actions of a universal machine is its ISA. This ISA is complete. Consequently, when we say that an ISA is complete, it is the same as saying that we can build a universal machine exclusively based on a given ISA. Hence, we can solve the problem completeness of an ISA by solving the problem of designing universal machines. They are dual problems. It is easier to reason in terms of using universal machines. Hence, let us delve into this problem. Computer scientists started pondering at the design of universal machines at the beginning of the 20th century. They wanted to know what is computable and what is not, and the power of different classes of machines. Secondly, what is the form of a theoretical machine that can compute the result of all possible programs? These fundamental results in computer science form the basis of today's modern computer architectures. Alan Turing was the first to propose a universal machine that was extremely simple and powerful. This machine is aptly named after him and is known as the Turing machine. It is merely a theoretical entity and is typically used as a mathematical reasoning tool. It is possible to create a hardware implementation of a Turing machine. However, this would be extremely inefficient and require a disproportionate amount of resources. Nonetheless, Turing machines form the basis of today's computers, and modern ISA are derived from the basic action of Turing machine. Hence, it is very essential for us to study its design. Note that we provide a very cursory treatment in this book. Interested readers are requested to take a look at some seminal text on theory of computation. The general structure of a Turing machine is shown in figure 1.6. Okay, a Turing machine contains an infinite tape that is an array of cells. Okay, so infinite tape, which is an array of cells. Each cell can contain a symbol from a finite alphabet. There is a symbol, a dollar, that works as a special marker. A dedicated tape head points to a cell in the infinite tape. It is a small piece of storage to save the current state among a finite set of states. This storage element is called a state register. So particular state is stored in the state register. A dedicated tape head points to a cell in the infinite loop. There's a small piece of storage. And there's a finite set of states. The operation of the Turing machine is very simple. In each step, the tape head reads the symbol in the current cell, its current state, from the state register, and looks up a table that contains the set of actions for each combination of symbol and state. This dedicated table is called a transition function table or action table. Each entry in this table specifies three things: whether to move the tape head one step to the left or right, the next state, or the symbol that should be written in the current cell. Wait, I will just still use this. So we have an infinite tape, right? And then we have the tape head. I should do this. Head. And then we have state register, which stores the current state. And then this dedicated table called transition function or action table. Each entry in this table specifies three things. Specifies three things: whether to move table head one step left or right, move tape head the next state. What do they mean the next state? The symbol that should be written in the current cell. the next state symbol to be written in current cell. So it can contain either of these three instructions. Thus, in each step, the tape head can overwrite the value of the cell, change its states in the state register, or move to a new cell. Change state in state register. The only constraint is that the new cell needs to be the immediate left or right of the current cell. For many, its format is the state symbol, left, right, new state, new symbol. Okay, so state, given our state and symbol, we either move left or right. We either change the state in the thing, in the state register, and we write the new symbol to the cell. Design a Turing machine to increment a number by 1. Each cell contains a single digit, so here's an infinite tape. This is a special character. Wait, I should write special marker, maybe. Marker. The number is demarcated at both ends by the special marker. Lastly, the tape head points to the units digit. We first define 4 states S0, S1, pre-exit and exit. I don't understand the difference between the state and symbol. Current state, this symbol that works as a special marker. Current state among a finite set of states is stored in the state register. The computation is over when the Turing machine reaches the exit state. The states S0 and S1 represent the value of the carry 0 or 1 respectively. The state register is initialized to S1 since we are incrementing the number by 1. In other words, we can assume that the starting value of the carry digit is equal to 1. At each step, the state head reads the current digit D and the value of the carry C from the state register. Okay, so it reads 9 and it reads what's stored in the state register, in which case it's 1. For each combination of D and C, the action table contains the next state and the result digit. Tape head always moves to the left. For example, if DC is equal to 9, 1, then we are effectively adding 9 plus 1. DC for each DC. The next state is equal to S1. The Turing machine writes 0 on the current cell and the tape head moves to the cell on the left. The only special case arises when computation is ending, when the tape head encounters the AND symbol, then it looks at the value of the carry. If it is equal to 0, then it leaves the value untouched and moves to the exit state. If it is equal to 1, then it moves to the pre-exit state, writes 1 to the cell, and moves to the left. Subsequently, it writes dollar to the cell under the head tape and then moves to the exit state. Okay, I'm still confused by the difference between state and symbol. Each cell can contain a symbol from a finite alphabet. There's a small piece of storage to save the current state among a finite set of states. So the tape head reads the symbol in the current cell, its current state from the state register, and looks up a table that contains a set of actions for each combination of symbol and state. State and symbol. For each combination of T and C, the action table contains the next state. So for this example, D is the state and C carry is the C contains a symbol, right? Okay, let's read the next example. Design a Turing machine to find out if a string is of the form A, B, 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 B. Let us define two states, SA, SP, and two special states, exit and error. If the state becomes equal to exit or error, then the computation stops. The Turing machine can start scanning the input from left to right as example 2. It starts in state SP. The action table is as follows. So B, what is this? New symbol, new state, left, right. Left, SPB. Okay, wait. So if the state is SP and it's reading a B, then it goes left, SP, then it goes left, state remains SP, and then it writes P. Okay, wait. So if it reads B over here, the tape head writes P, goes to the left, and the state in the state register is SP. And this goes to the left. If the current state is SP and it encounters an A, then the state changes to this goes to the left, this goes to A, this goes, yeah, and this is written, A is written here, so no changes are made. If it encounters an A again, A is written over here, this goes to the left, and SA, the state remains SA. So if it encounters an A, the state is SA. Nothing is written, nothing is rewritten, and it goes to the left. A is rewritten, but there would be no changes. However, if it encounters a B, then there is an error, and that's an error state. So if it's in state SA and it encounters a B, then move left, error, and then B. If it's SB and it encounters a dollar, then move left, error, and then dollar. Because it's not supposed to be starting at B, right? It's not there isn't supposed to be a dollar here. It is supposed to be a dollar here, like before the A's, not before the B's. So if the state is A, there's a dollar, then exit. State is A, then it's normal. Okay, I understood this part. Design a Turing machine to find out if a strong string, if a string of characters is a palindrome. Palindrome is a word that reads the same forward and backward. For example, civic, rotator, rotor, further. Assume each character is either A or B. Okay. So each character is either A or B. Okay, this one is quite complicated. Let us assume that the Turing machine starts at the rightmost character in the begin state. Let us consider the case when the symbol is under the tape head. Symbol under the tape head is A in the begin state. The machine enters the state LA. Starting symbol is A, replaces A with $sign. Now it needs to see if the leftmost character is A. Okay, so wait. If it reads A, then the state is SA. There's a $sign here. $sign here. State is SA. Actually, if it reads, let's do this. If it reads A, write A over here, go to the left. So this state, when the Turing machine is in this state, this arrowhead needs to go all the way to the left. So if this is the state, whether the arrowhead reads A or B, A or B, just keep going to the left. A or B, just keep going to the left until it encounters a $sign. If it encounters a $sign, then go one back right. And then if the state is LA, then check if there is an A over here. If not, send an error. So there should be an A over here, send an error. Yeah. And then this comes a $sign. And then this comes a $sign. Now we go right one. It's either, so the states can be LA, RA, LB, RB. So the state can be, or we need two extra states. So if it goes to the end, it needs to go one back. Like when it reads the $sign, it needs to go one to the left or one to the right. So that will create more states. So anyways, if for example it reads a B, change the B to a $sign, and then this will be B. So this over here means whether you read A or B, keep going to the right. Keep going to the right until a $sign is encountered. If the $sign is encountered, go left one. go left 1, and there should be a B. If it's a B, replace it with a dollar sign. Or if it's not, then send an error. I think this is the best way I can explain it. The machine enters the state LA, move left, starting symbol is A, replaces A with dollar sign. Now it needs to see if the leftmost character is A, hence the tape head moves towards the left until it encounters dollar. It then enters or check A state. It moves one cell to the right and checks if the symbol is equal to A. If it is A, then the string might be a palindrome. Otherwise, it is definitely not a palindrome. The procedure can terminate by entering the error state. The tape head again rewinds by moving all the way to the right and starts at the cell which is towards the immediate left at the starting cell in the previous round. The same algorithm is performed iteratively till either an error is counted or all the symbols are placed with dollar signs. The starting symbol was B, then the procedure would have been exactly the same, albeit with a different set of states. LB or check B. The action table is shown below. This one is quite complicated. In these examples, we have considered 3 simple problems and designed Turing machines from them. We can immediately conclude that designing Turing machines for even simple problems is difficult and cryptic. The action table can contain a lot of states and quickly blow out of size. However, the baseline is that it is possible to solve complex problems with this simple device. It is in fact possible to solve all kinds of problems, such as weather modeling, financial calculation, and solving differential equation with this machine. Church Turing thesis, any real-world computation can be translated into an equivalent computation involving Turing machine. This observation is captured by the Church Turing thesis, which basically says that all functions that are computable by any physical computing device are computable by a Turing machine. Layman's terms, any program that can be computed by deterministic algorithms on any computer known to man is also computable by a Turing machine. This thesis held its ground for the last half century. The researchers have up till now not been able to find a machine that is more powerful than the Turing machine. This means that there is a program that can be computed by another machine and not by a Turing machine. There are some programs that might take forever to compute on Turing machine. However, they would also take infinite time on all other computing machines. We can extend the Turing machine in all possible ways. We can also consider multiple tapes, multiple tape heads, multiple tracks in each tape. It can be shown that each of these machines is as powerful as a simple Turing machine. The Turing machine described in section 1.6.2 is not a universal machine. This is because it contains an action table which is specific to the function being computed by the machine. A true universal machine will have the same action table symbols and also the same set of state for every function. We can make a universal Turing machine if we can design a Turing machine that can simulate other Turing machines. This Turing machine will be generic and will not be specified to the function that is being computed. Let the Turing machine that is being simulated be called M and the universal machine be called U. Let us first create a generic format for the action table of M and save it in a designated location or tape of U. This simulated action table contains a list of actions and each action requires for the 5 parameters. Old state, old symbol, direction, old state, old symbol, direction, new state, new symbol. We can use a common set of basic symbols that can be the 10 decimal digits. If a function requires more symbols, then we can consider one symbol to be contained in a set of contiguous cells and demarcated by special delimiters. Let such a symbol be called a simulated symbol. Likewise, the state in the simulated action table can also be encoded as a decimal number. For the direction, we can use 0 for left, 1 for right. Thus, a single action table entry might look something like this, where you have the old state, old symbol, direction, new state, new symbol. Here the at is a delimiter. This entry is saying that we are moving from state 1334 to 1335 if symbol 34 is encountered. We move left and write the value of 10. Thus, we have found a way of encoding the action table set of symbols and states of a Turing machine designed to compute a certain function. Similarly, we can designate an area of the tape to contain a state register of M. We call this the simulated state register. Let the tape of M be given a dedicated space in the tape of U. And let us call this space the work area. The organization is shown in figure 1.7. Layout of a universal Turing machine. So work area, simulated action table. Oh, so in the work area, I think, wait, this tape is thus divided into 3 parts. The first part contains a simulated action table. Second part contains the simulated state region. Simulated, okay. The last part contains the work area. So I think the universal Turing machine will work here. If it wants to do some work that contains like a simulated machine, it can like switch over here to the simulated machine work and use this register for as the state register for the simulated machine. And then when it's done over here, it can go back to the work area and then go to a new simulated machine. The universal Turing machine has a very simple action table and set of states. The idea is to find the right entry in the simulated action table that matches the value in the simulated state register and simulated symbol under the tape head. Then the universal Turing machine needs to carry out the corresponding action by moving to a new simulated state and overwriting the simulated symbol in the work area if required. The devil is in the detail. For doing every basic action, you need to do tens of tape head movements. The detail are given in a hub graph. Okay, construct a universal Turing machine. It is possible to construct a universal Turing machine that can simulate any other Turing machine. Since the 1950s, researchers have devised many more types of hypothetical machines with their own sets of states and rules. Each of these machines have been proven to be at most as powerful as the Turing machine. It is a generic name for all machines and computing systems that are as expensive. Such systems are said to be Turing complete. As any universal machine, an ISA is thus Turing complete. Any computing system that is equivalent to a Turing machine is said to be Turing complete. Thus, we need to prove that an ISA is complete or universal if it is Turing complete. Wait. ISA. We need to prove that it is universal if it is Turing complete. A modified universal Turing machine. Let us now consider a variant of universal Turing machine that is more amenable to practical implementations. Let it have the following features. Note that such a machine has been proven to be Turing complete. The tape is semi-finite, extends to infinity in only one direction. The simulated state is a pointer to an entry in the simulated action table. There is one unique entry in the simulated action table for each state. While looking up the simulated action table, we do not care about the symbol under the tape head. An action directs the tape head to visit a set of locations in the work area and based on their values, computes a new value using a simple arithmetic function. It writes this new value into a new location in the work area. The default next state is the succeeding state in the action table. An action can be arbitrarily can also arbitrarily change the state if a symbol at a certain location on the tape is less than a certain value. Changing the state means the simulated tape head will start fetching actions from a new area in the simulated action table. So state pointing to action table entry, table head, work area, read, compute, right? So it's infinite only in one direction. Simulated state is a pointer to an entry in a simulated action table. An action directs the tape head to visit a set of locations in the work area based on their values and computes a new value using simple arithmetic function. Writes this new value into a new location in the work area. So it computes the new location. The default next state is a succeeding state in the action table. An action can arbitrarily change the state if a symbol at a certain location on the tape is less than a certain value. Changing the state means the simulated tape head would start fetching actions from a new area in the simulated action table. This Turing machine suggests a machine organization of the following form. There is a large array of instructions. Action table. This array of instructions commonly referred to as the program. There is a state register that maintains a pointer to the current instruction in the array. We can refer to this register as the program counter. It is possible to change the program counter to point to a new instruction. There is a large work area where symbols can be stored, retrieved, and modified. This work area is also known as the data area. The instruction table in the work area was saved on the tape in a modified Turing machine. In the practical machine, we call this infinite tape as the memory. Memory is a large array of memory cells where a memory cell contains a basic symbol. A part of the memory contains the program, and another part of it contains data. So, large array of instructions, which is this, which is the program basically, is a state register that maintains a pointer. You can refer to as the program counter. So this over here is the program counter. Large work area is the data area. This over here is the data area. And then this entire thing is the memory. What about the generic state register? The memory in our conceptual machine is a semi-infinite array of symbols. A part of it contains the program consisting of basic instructions, and the rest of it contains data. Data refers to variables and constants that are used by the program. Furthermore, each instruction can read a set of locations in memory and compute a small arithmetic function on them. Write the results back to the memory. It can also jump to any other instruction depending on values in the memory. There is a dedicated unit to compute these arithmetic functions, write to memory, and jump to other instructions. This is called CPU. Figure 1.9 shows a conceptual organization of this machine. Program counter, control unit, arithmetic unit, program data. So the program, wait, so the program is a simulation of this data. It's like not simulation, it's like the real world implementation. Data is the entire thing. Data is the implementation of this. The control unit, arithmetic unit. the program counter. The program counter decides where to go next in the program, like the next instruction. Interested readers might want to prove the fact that this machine is equivalent to a Turing machine. It is not very difficult to do so. We need to know that we have captured all aspects of a Turing machine: state transition, movement of the tape head, overwriting symbols, and decision based on the symbol under the tape head. Figure 1.9 represents a universal machine that can be practically designed. Let us now try to design an ISA for our modified Turing machine. We should see that it is possible to have a complete ISA that contains just a single instruction. Let us consider an instruction that is compatible with our modified Turing machine and has been proven to be Turing complete. SNB stands for subtract and branch if negative. Here A and B are memory locations. This instruction subtracts B from A, save the result in B, and saves the result in A. So B subtracts B from, so it's A minus B, and if A is less than 0, go to C. Okay, otherwise the control transfers to the next instruction. For example, we can use this instruction to add two numbers saved in locations A and B. Note that exit is a special location at the end of the program. SN subtract branch negative. Okay, subtract branch of negative. Temp B A, temp minus B. If temp is less than 0, go to 2. Subtract branch of negative. A minus temp. If A is negative, go to exit. Here we assume that the memory location temp already contains the value 0. The first instruction saves minus B in temp. Irrespective of the value of the register, it jumps to the next instruction. Note that the identifier number is a sequence number for the instruction. The second instruction, we do A minus temp. But temp is minus B, so it's A minus minus B. So we get A plus B, right? But A plus B is not negative. Thus, we have successfully added two numbers. We can now use this basic piece of code to add numbers from 1 to 10. Assume that the variable counter is initialized to 9, index is initialized to 10, 1 is initialized to 1. Right, temp, go to 2. Temp, index, go to 3. Wait, if temp is 0, the 0 count, it says if negative, right? If A is less than 0. So what happens if temp is 0? Counter is initialized to 9. So this is 9. Index is initialized to 10. So this here is 10. 1 is initialized to 1. So this here is 1. Okay. So temp 2 goes to the next instruction, which is 2. Temp index 3. Index is initialized to 10. So 0 minus 10. And minus 10 stored here. And then 3, we have sum. Sum is 0. Sum minus minus 10. So it's 10. And then we have index and 1. 10 plus 1. 10 plus 1 is 11. Sorry, temp minus 1 is 9. And then counter, which is 9. Counter minus 1 is 8. And then temp 7. then temp 1, 1. Okay, I don't understand. We observe that this small sequence of operations runs a for loop. The exit condition is in line 5. The loop happens back in line 7. In each iteration, it computes minus sum plus index. There are many more similar single instruction ISA that have been proven to be complete, such as subtract and branch if less than or equal to, reverse subtract and skip if borrow. Writing a program with just a single instruction is very difficult. Programs tend to be very long. There is no reason to be stingy with the number of instructions. We can make our life significantly easier by considering a multitude of instructions. Let us try to break up the basic S and B instructions into several instructions. So arithmetic instructions, we can have a set of arithmetic instructions such as add, subtract, multiply, divide, move, move values across different memory locations. They should allow us to load constant values into memory locations. Branch, decode a branch instruction that change the program counter to point to new instructions based on the results of computations or values stored in memory. Keeping these basic tenets in mind, we can design numerous types of complete ISAs. The point to note is that we definitely need 3 types of instructions: arithmetic, move, and branch. In any instruction set, we need 3 types of instructions: arithmetic, data transfer, so move, and then branch. Let us summarize the main results that we have obtained from our short discussions on theoretical computer science. The problem of designing a complete ISA is the same as that of designing a universal machine. Universal machine can run any program. We can map each instruction in the ISA to an action in the universal machine. Universal machine is the most powerful computing machine known to man. If a universal machine cannot compute the result of a program because it never terminates, then all other computing machines are also guaranteed to fail for this program. Universal machines have been studied extensively in theoretical computer science. One such machine is the Alan Turing machine, named after the father of computer science, Alan Turing. The Turing machine is a very construct computing device and is not amenable to practical implementations. Practical implementation will be very slow and consume a lot of resources. However, machine equivalent to it can be much faster. Any such machine, ISA, and computation system that is equivalent to a Turing machine is said to be Turing complete. We defined a modified Turing machine that is Turing complete in section 1.6.4. It has the structure shown in figure 1.10. Its main parts and salient features are as follows. We already read that. A simple one instruction ISA that is compatible with our modified Turing machine contains the single instruction SPN. Subtract, branch if negative. We can have many Turing complete ISAs that contain a host of different instructions. Such ISAs will need to have the following types of instructions: arithmetic, move, and branch. How much is left? Okay, you know what? I will read this chapter, this section in the next stream, because it's getting longer than expected. So I'll end the stream here. And like, what should I do? Like, I was thinking of me writing some notes and then releasing it in the comments, but I don't know if I'm allowed to do that. I will try doing that next stream if I'm allowed to, but otherwise, I won't make any notes. Anyways, see you guys next time. Bye.